Hi everyone. It is January 30th and we're not having class tonight because of the brutal cold. So, uh, because I had a little bit of time, I learned how to make videos, record videos off my laptop, load them to YouTube, and so that you can listen to these, gain knowledge, all in the comfort of your home while wearing your underpants. So here we go. This is wrapping up the last section of PV 101. And so listen to this, understand the material, and then I want to do a couple activities based on this information. So this section is on array sizing and production estimates. We've done this in class prior to this section. Okay, determining the array size. Well, first we're going to use a load profile, and we're going to determine how much energy is used on an annual basis, and then whittle that down to a daily basis. So first off, I'm going to gather up 12 months of utility bills, add them all up together, divide them by 365 to get a daily load, and that will be in kilowatt hours because the utility gives me information in kilowatt hours. Here I have an imaginary utility bill. This is my average per day consumption right here. And it gives me 2 years, 2013 and 2014, side by side, so I can see how I did in comparison to last year. ComEd, I know from my bill, it gives me the last 12 months of use, and I can compare this month to a year ago. How does it look? Charges, let's see, here's our charges over here. Let's go back down here. Below the daily use, here's the monthly comparison, comparing 2014 October to 2013 October. 2014 we used 1404 kilowatt hours. In 2013 we used 1 kilowatt hour more. So pretty much the same. The average temperature was same, and our consumption was essentially the same. Where is the information? So I used 1,405 kilowatt hours, or 4 kilowatt hours. So here is my electric supply charge right here. So that's about 10 cents a kilowatt hour. And then utility charges, $60 on top of that. So each utility has a different billing scheme, and as I saw in one of the classes that you folks were in, I think the one that Matt and Glenn were in, um, we saw the same bills from the same utility, and I think there was 3 different billing schemes going on there. And so we're going to get a charge, nonetheless, we're going to get a charge for the electricity, and that cost could be anywhere from like 4 cents to $1.25 per kilowatt hour. Around here at ComEd territory, you're going to pay 6.5 cents per kilowatt hour. In addition to that, there's going to be all these other hidden fees. These hidden fees are the things that they don't tell you about, like a customer service charge. So you're going to have a meter fee, maybe 20, 30 bucks a month, where there's a line item on your bill, meter fee or customer service charge, and that's having the honor of having that meter on the side of your house and have somebody drive by and collect the data digitally off that meter. On the ComEd bills, there's a transmission and distribution charge. So there's like another 6.5 cents that we are charged for transporting those electrons through the transmission cables to your house. And I get why. I get that utilities are going to break down, nickel and dime you on these charges, but and I realize and understand that they have to maintain their infrastructure, but I think it is, I feel that the cost of electron is the cost of electron, that it includes the flat fee for the customer charge, having a meter on your building. It includes the transportation to your house as well. And if you use more, well, then you pay more. And so they nickel and dime us on all these different costs, and then the grand total ends up being significantly more than that 6.5 cents we paid for that kilowatt hour. In this case, this customer, I'm reading down for their PPL electric utilities price to compare for your rate is 0.08956 cents per kilowatt hour. So that's what they're paying. They're paying that rate, but then there's this other rate, utility charges, that's a flat fee that they see all the time, regardless if they use 5 kilowatt hours or 5,000 kilowatt hours. And at the end of the day, they pay $172.81. So what I'm trying to get at is if we take this, actually, let's take that. If I consume, it's costing me $172.81, and I'm using 1,400 kilowatt hours per month. That's the real cost of that electricity is 12.3 cents per kilowatt hour, not 8.9 cents per kilowatt hour. So when we do our financial analysis, we have to base our financial paybacks based upon the rate of the electricity, or this 8 cents, 8.9 cents, not the 12.3. And so the national trend is to shift to lower cost electricity. So, for instance, going from 12 cents a kilowatt hour down to 6 cents a kilowatt hour, but then raising the flat fees or the customer charges, raising those up to compensate for any of those losses or more. So now it makes it even less attractive for us to put in a renewable energy system. We just doubled the time for it to pay, in quotes, pay for itself. And I think that's dishonest, quite honestly. So buyer beware. Take a look at your utility bill. What are you being billed for? What is the rate? How does that compare from year to year? There may be even seasonal charges associated with that as well. All right, so here is 12 months of utility bills all added up to a grand total of 5,876 kilowatt hours per year. So this is like 50% of the average, in quotes, average American home in the United States. And if you remember, we said that the average American home consumes around 10 or 12, 11, 10 or 11 or 12 kilowatt hours per year, 1,000 kilowatt hours per year, and this is half of that. So we take that grand total for 1 year, divide by 365, and it gives us 16.1 kilowatt hours per day consumption. Now we're going to step aside and find out the peak sun hours, or the kilowatt hours per meter squared per day, what the resource is at our location, and this is latitude specific. So I go through and I do the put in my zip code, and I'm in PV Watts, put in my zip code, and put in, I model out a 1 kilowatt system, and either way, I want to get to this page. This is the output page, and I think they just, whoever did this PowerPoint modeled the default setting for the zip code of 54423. And this is what we're looking for. We're looking for this number right down here, the one that's circled. We're looking for the average annual 4.3 sun hours per day, or we could say 4.3 4.3 kilowatt hours per meter squared per day. That's our solar resource. So it's saying that we have an average of 4.3 hours of the day that we have 1,000 watts per meter squared. And and if you remember from lecture, that's cumulative over the time of the day from sunup to sundown. So we take step 3, we take our daily consumption and we divide that by our daily solar resource, in this case 4.3 cent-hours per day. And then we're going to and that'll give us a number. And actually, let's bang that out real quick. Let's see. 16.1 divided by 4.31 cent-hours. And then that'll give me a number of 3.7 kilowatts. So I got rid of the hours, I got rid of time, and I'm just looking at power. And so if I divide 16.1 by 4.31 cent-hours, I get 3.7 kilowatts. But that number is just on the AC side. Now I have to bump that number up 20% to compensate for inefficiencies in the built into the system. Wire losses, module mismatches, converting DC to AC, stuff like that. So I'm going to bump up that number by 20%, and that's a standard number. Used to be 23%, but we still use 20% when we do this calculation. Now it's more like 18%, but we still use 20% because it's a nice round number. So we're going to do that. We're going to bump it up 20% by dividing this 3.7, I believe it was, 3.7. We're going to divide that by another 0.8. So I'm going to divide that by 0.8, and I get a new number. And that number, by the way, is 4.6 or 4.66 kilowatts or 4.7 kilowatts. So of DC array to make that 5,800 and some kilowatt hours on the AC side annually. So I'm going to overproduce in the summertime, underproduce in the wintertime, and it all evens out. Here are some of the things that we where our losses are when we run these numbers. When we bump it up 20%. Wire run, electrical connections, heat, DC to AC, heating. This could be the physical heat on the side of the building that's warming up the inverter out in the hot sun above 122 degrees. The electronics, efficiencies, snow loading on the array, dust and dirt, module mismatch, photo degradation, shading, and then grid availability. So here's my new number. I take the daily load divided by the daily resource, bump it up 20% by dividing by 8, and I have a 4.7 kilowatt PV array. That's what would be needed to meet the annual load. Here's another one. So why don't you take and add this one up real quick. Get those calculators out. I should hear them clicking. Jacob. All right, good job. So here is the new load for a new location. So my new annual load is 5,411 kilowatt hours per year. And again, how does this compare to the national average? Well, it's about half, right? So step 2, what is step 2? Right, correct. Divide by 365 to get a daily load. So I divide 5,411 by 365, and I get a daily load of 14.8 kilowatt hours per day. I go to PV Watts, and our location is Phoenix, Arizona. I put in the zip code for Phoenix, Arizona. I model out in PV Watts a 1 kilowatt system, 1 kilowatt here, standard module, fixed roof mount. If it's ground mount, then I would model a ground mount. System losses, is default is 14%, but if you remember, I said the system losses are 20%. Well, on PV Watts, for whatever reason, I don't know why they did it, but anyway, we see 14% on this side of the chart, but on the back side of the chart, we see an additional 6% that is going to be used for inverter losses. And if you click this little eye right here, that's where you will see that number. So this is still 20%. So mentally get rid of that 14%, put in 20% mentally. Tilt angle, let's just leave it at 33 degrees, and I would reckon that that is latitude. And then azimuth of 180 degrees south. Click go. Next up, this is what 1 kilowatt of PV will do in this environment at that azimuth, at that tilt angle. Here I have the production number for a 1 kilowatt system by each month for a grand total. And then in this column is my solar radiation, or my solar resource sources per month, and then an average, 6.57 sun hours per day, or I could say 6.57 kilowatt hours per meter squared per day. I'm still going to use my 20% losses. So I take my 14.8 kilowatt hours per day, divided by my solar resources, 6.57 hours per day, divide by 0.8 to bump it up 20%. So I would need a 2.8 kilowatt system to meet my needs. That is absolutely bizarre. And we scoped out one for a Midwest system, and that was essentially double that size. So let me run this number real quick. 6.57 divided by 0.8 equals, yep, son of a gun. That's crazy. Well, long story short, they need half the amount of modules to do the same amount of work in Arizona as in the Midwest. So that's what you can do. That's a quick and easy way to size an array based upon the 12 months of utility bills, based upon this ballparking method, which is actually quite accurate. But we have to take into consideration it doesn't. It assumes that there's 100% solar radiation all the time, 24 hours a day, 7 days a week, or so many hours a day, 7 days a week. And it doesn't take into accounting shading. And to be more accurate, we have to add in the shading. So for determining an array for a new house, there's a couple of different methods. I can look at the past consumption of the home over 1, 2, 3 years. Look at that data, see if there's any trends of increasing use, decreasing use. I can look at the age of the family, how many members are in the family, and make assumptions based upon that. I can look at their appliances and make assumptions on that. But if they're building a new house, well, are they taking the old appliances with them, or are they getting new appliances? Here's some suggestions for lighting. Here's some suggestions for appliances. And so you're going to have to ballpark it. Standalone system. For a standalone system, we're going to take and make a highly accurate daily load profile. So we're going to go through and make an inventory of everything electrical that we need to run on a daily basis. What is the object? What is the consumption in watts? How long does it run? And come up with a watt-hour estimate of our consumption on a daily basis. Then we're going to take that number and size a battery pack. And the battery pack, again, is we only have 50% available to us. And so we already have to double the size of the battery pack. Plus, we're going to have 3 or 4 days of autonomy. So now we're going to take that battery pack that we originally were going to size for the needs. Then we double it because we only have access to 50% of the capacity. Then we're now going to times that by 3 or 4 so that we have 3 or 4 days of autonomy without resource. We're assuming that at some time during the year that we aren't going to have enough solar resources to charge our batteries. So this battery pack is going to be grossly oversized for most of the year and get us to squeak by through the good times, through the bad times. Then we're going to take and size an array to meet the needs of that battery pack. And so the PV array is going to be grossly oversized because it's going to be sized for the PV array at its greatest need and the lowest amount of resources. And that's going to typically be maybe November, December, January, that time period. And it's just going to be grossly oversized. In the summertime, it's just going to sit there waiting to do something. So for the best accuracies, the back of the napkin method is really good, but you have to be reminded that shading is not calculated into that. Method number 2, which we already did in class or will do in class, is to take PV watts, run the numbers, model out a 1 kilowatt system to get at a certain tilt angle, at a certain azimuth in the zip code that you're working with, and then laying out the numbers by month. Then take and do a Solar Pathfinder assessment to determine what the shading is at that site, and then redo the numbers from PV watts, the monthly outputs, versus the shading taking place at a particular month, and then coming up with a new annual production for that 1 kilowatt system. And that one is highly accurate as well. And that takes into consideration when you use PV watts and a Solar Pathfinder or a shading analysis tool, using those two together in tandem makes a highly accurate prediction on what the system will produce or how much you need. All right, PV financial modeling. This is, I think what I'm going to do is I'm going to run through this, but then I'm going to break this out as a separate unit so that when we get into site assessment that you can come back to this and review it, because I'm going to expose you to some terms that you may not be familiar with or won't be familiar with, and we're not going to bat them around like we do other terms, these other $5 words. We're going to use them like after spring break. So I'll run through it, but be aware that I'm going to take and break this section down into its own for when we get into site assessment. And you can review that at your leisure, once again, with a cup of coffee, sitting in your underpants on Sunday morning. All right. So, what is the cost of PV? Well, it varies based on size, based on complication, where is it located, is it on the roof, is it out in the backyard, is there trenching, how difficult is it to get from point A to point B? And all that is taken into consideration, and you come up with this cost. And this cost is called dollars per watt. And that includes labor, parts, materials, everything. You hire a company to do the work, and you sign a check and give it to them when they're done. And this dollar per watt includes everything associated with that installation, permitting, everything. So on the high end, a solar electric system, utility intertie system, no batteries, is going to cost around $3 a watt or less. The more complicated it is, or the further away it is on a ground-mounted system, the higher that cost is going to be. The more straightforward that is, the less the cost is going to be. The shop I work for takes on all the complicated systems, residential and commercial, and so our shop charges a premium for that. So we're at or a little bit above $3 a watt. Competitors who take all the simple, straight salt box, south orientated garage installations that you can get in and out in a day, well, they can do that for a little over $2 or $2.50 a watt. Um, utility utility size systems, you can put food on the table at $1.70 watt, and now it's down to as low as $1.20 per watt, which is absolutely amazing. Wind power, in comparison, wind power is about $1 a watt. Incentives. Each state has its own regulations, its own rules, its own incentive programs, and you're going to find that information out by going to desertusa.org. So you're going to go to that website, and it's maintained by the University of North Carolina, and it's updated on a regular basis. So you go into it, go to your state, click on that, and it has all this cool information on energy efficiency programs, utility rates, solar access laws, net metering laws, um, bloody, bloody, blah. So that's the go-to place for all your information. Some definitions. You should know this definition because we've been through it a number of times. This is one of those $5 words. Net metering. So this is a billing scheme where I am allowed through federal legislation that all investor-owned utilities must allow me to hook up to their system and store my excess energy on the grid at retail rates and then buy that back at retail rates. But there's going to be some hurdles or goalposts I have to go over. Like I may have a certain amount of capacity or rated output that I can only go up to, and then I fall into a different category where I store at wholesale and buy at retail. Sometimes these billing schemes are trued up each month, so whatever I produce offsets what I consume. Anything left over, I'm compensated at wholesale rates. Other schemes, it may true up annually, it may true up quarterly, it may true up monthly. It depends on who the utility is. So read the fine print. In Illinois, this is the net metering category for Illinois, and if you go to Desert USA, you'll see this information. So here we are, Illinois, net metering. Here is the website for net metering on the PSC, the date that it was implemented, what technologies it applies to. So PV, wind, biomass, hydroelectric, anaerobic digestion, fuel cells, and microturbines. And then what sector? Commercial, industrial, local government, nonprofit, residential, school, state government, federal, ag, institutional. Let's see, investor-owned utilities, alternative retail electric suppliers. Here we go, system capacity. So I can build a system, PV system, or a wind system, or a microturbine system, or a biomass system, up to the rated output of 2 megawatts and fall into the net metering scheme. So I can store my excess energy on the grid in the form of a credit or be compensated for overproduction, what I don't use, and at retail rates. And that's pretty big. That's enough to like supply the energy for several hundred homes. So that's pretty. That's Illinois has something going for it there. Feed-in tariffs. On occasion, there are these additional costs that I can reap by putting out renewable energy onto the grid. So the utility may buy everything I produce and then at a premium rate, maybe 25 cents or 30 cents or 20 cents or whatever that is, and then I'm going to buy at retail rates. So I'm going to have 2 meters, 2 meter fees. I'm going to have a buy meter that supplies my house, and a sell meter which sells everything I produce out to the grid. And these are nice billings. These are nice programs if you can get in on them. The state of Illinois is going to have some sort of program coming out. Nobody knows because there's a great big giant question mark for the last 2 years. And the last time I heard last month that it's just about ready to come out. And I heard that 6 months ago too. So, well, welcome to the solar coaster. State programs. State of Illinois has again this FEJA program. The nuclear power plant um, wasn't decommissioned, so this is their pendants, and there's a bunch of money available for systems going out on the grid. What was it like 3,000 megawatts for the next several years? And so anyway, there's state programs that are available too, and I can find out about that on Desera USA. Utility rates. We talked a little bit about this in the beginning of basic PV. So there's the customer charges. Those are the charges that are going to be associated with like meter fees, distribution fees, service fees. That's a fixed cost. Um, generally a fixed cost, and then there could be another cost based upon what you consume. Energy charges, that generally means the cost of the electricity that you're buying, and it's going to be a rate of like somewhere between maybe 4 cents and $1.25 maybe. And then demand charges. These are above and beyond what you use. So these customer charges, as I said, are meant to recover costs, fixed costs for the utility, and aren't factored into the cost over the overall kilowatt hour. That's where I was getting all upset about before. So meters, meter reading, billing, maintenance, all that stuff I'm getting charged for in a monthly service fee. So they're guaranteed a certain amount of money per month from you. Where I used to live, I was paying I think $20 a month for a service fee, and my entire utility bill was like $30 a month. In their they put a proposal to the Public Service Commission, the three appointed people who oversee the investor-owned utilities in the state, and my utility went to the Public Service Commission and said, "Okay, this is what we're going to do. We have the most expensive electricity in the state, 14 cents a kilowatt hour. We're going to drop it down to like 10 cents, but we're going to raise up the meter fee, and we're going to do it. We're going to implement that incrementally, and at the end of the day, had they been able to implement that, my meter fee, my fixed cost would be $69 a month minimum. So I would have the fixed cost would be greater than I was paying right now with the fixed cost and all my electricity, and that's just a bunch of garbage. Here's some more on the fixed flat fees. Um, and this isn't figured into the cost of the kilowatt hour, and that doesn't get calculated into the financials of my system either. Energy charges, and so this is the retail rate of what I'm going to buy this electricity at, and this could be just a flat rate. So it's the same amount of money for that kilowatt hour if I consume 100 kilowatt hours or 100,000 kilowatt hours. But then there may be block structures too, where I pay a certain rate from 0 to 500 kilowatt hours a month, and another higher fee for like 101 or 501 to 1,000 kilowatt hours per month. And then maybe from 1,001 kilowatt hours to 2,000 is a separate rate. So different tiered rates. And again, there could be seasonal charges in there. I may get charged more for the summertime electricity than the wintertime. all sorts of stuff in that's hidden into these numbers. Demand charges are typically something that is more of a commercial or industrial application. So, um, so this is not only the energy you consume over the year, over the month, but also the power, the maximum power you draw in a certain amount of time, and that could be 5 minutes, 10 minutes, 15 minutes, and whatever that max power draw. So power is just volts times amps, right? It's not energy over time. Power over time is energy. They're looking at your largest draw, and there used to be an analog needle that would swing up and peg to a certain max point, and meter reader would come, read the meter, and then look at this demand needle, and then you would have this multiplier on your bill. So if you, for instance, had a relatively low utility bill, you were managing your loads, but then for whatever reason you had this large air compressor that you would turn on for something. I don't know why, but you would. And it was a large draw. And so when this motor starts up, it has a huge inrush of current into the motor. And so volts times amps equals power. So you have this huge power inrush before the motor starts up, and it's just instantaneously. And that needle is going to peg out to a certain number, and you would be billed at a different rate because of this excess power draw. That only happens like 5 or 10 or 15 minutes a month. And I know of this one machine shop, and factories do this too. I'm aware of this one machine shop in particular. They have all these lathes and milling machines and everything, and they don't turn their equipment off at all. They keep running 24/7, and they do that because it's too expensive to shut them down and then start them back up on Monday. And so these demand charges are an adder, so it just bumps up my additional fees. So on this particular bill right here, I'm looking at, here's a time of use billing, here's a demand billing. So this is that power. So they're looking at an additional, this is like an additional $11, $3, oh, $11. And I don't know how that is added in, but mathematically, you don't want to be doing this. This does not want to be your bill. Oh, demand charges right here. $10,000 extra. So 40%, 45% of their electric bill is these unmanaged power consumptions, periodic, intermittent power draws that spike their bill up by 45%. That is absolutely amazing. So if we put a solar electric system on this factory or this machine shop or whatever it is, our solar electric is going to be producing electricity during the work hours, and that can lower the demand rates too. So we could possibly, instead of having a $10,000 demand fee every month, maybe we could whittle that down to 5,000. And over time, 5,000 times 12, that's 65,000 bucks per year, and that's like somebody's salary. That's more pencils. Cash flow analysis. Now we're kind of getting ahead of ourselves, but when we do a cash flow analysis, we're going to look at the cost of the system, the gross cost. We're going to subtract any state incentives, any federal incentives, any grants, and then subtract. Then we're going to have the net cost. Then we're going to then we're going to enter this net cost into this financial calculator, which I'll show you coming up in a few weeks. And we're going to compare that investment of, I don't know, $15,000 in a solar electric system and how much energy it's going to offset each year, what O&M fees are going to be associated with that on a regular basis, and then come up with some sort of number that system, or at some year, that system will be paying for itself and be cash positive. And it could be as little as 5 years if it's a commercial system. All commercial systems are paid off in 5 years. If it's a residential system, maybe it's going to be 5, 10, 12, 15 years. But at some point, this PV system is going to be paying for itself and more. It's going to be cash positive. So that's the analysis. And then we're going to compare that investment of that 15,000, we'll say, of net cost. We're going to compare that cost to or that savings to putting that $15,000 into a 30-year treasury bill. And so we're going to look at the two investments, PV or a treasury bill, on 30 years' time, and which one is going to be making more? What is my percent gain? 2 weeks ago, I looked up the return on investment for a 30-year T-bill, and that was like 3%. And so in 30 years' time, you're going to have 3% more than that 15%. And I guarantee that due to deflation of the dollar, inflation of costs, that that you may as well have just given me that 15,000. You'll have just as much now then as you will now. So these financial benefits, there's different ways of looking at the financial payback of a system, and it's all based upon different mathematical formulas and looking at the same problem from different angles mathematically. The first one is simple payback. What is the total cost of the system divided by how much you're saving, how much you're offsetting of that utility bill, and then you'll get a number of years of to recoup your costs. And really, this is just a fool's calculation. Why the hell would you do that? This system is going to be up on that rooftop for 30, 40, 50 plus years. And it doesn't take into consideration the cost of energy in that 30, 40, 50 years. Energy inflation runs at 4 to 7% per year. It doesn't take into consideration the devalue of the dollar. Doesn't take into consideration depreciation. Doesn't take into consideration of this, that, and the other thing. So this idea of doing simple payback is a bunch of crap, quite honestly. So don't do it. Other ways of looking at it, the good ways, is return on investment. So I'm going to take X amount of dollars that I'm going to be saving, and I'm going to divide it by my initial cost, and that'll give me my return on investment. So now this is going to be in a percentage, and so now I can take that percentage and compare it to the percentage of return on a T-bill. So the return on an investment of $11,500 is going to give me a 10.4% return on investment. But the return on investment on my 30-year T-bill, as I said a minute ago, was like 3%. So this is more than 3 times greater return on investment than a T-bill, the world's safest investment. So a way to think about this, how we think about this investment, we're taking all the electricity that this system will ever produce in its lifetime, all the maintenance, all the breakdowns, we're calculating that into our model, and we're buying that all up front at today's costs, at today's value of the dollar, and that's our fixed cost. We know what that cost is. Then we can take the production of that system in 30 years, for 30 years' time, divide that into the cost, and come up with the cost per kilowatt for that electricity. And I guarantee, even with this 6.5 cents per kilowatt hour here in Illinois, I guarantee that the electricity that you buy off this system in 30 years is going to be cheaper than utility power is today, right now today. I guarantee it. But we're only comparing it to 30 years. But the system's going to be up on the rooftop 40, 50, 60 years. We don't know because nobody's achieved this end of life yet. But this 30 years time is just a financial modeling method. We have to have some sort of date to say that this is the expectancy of this investment so that we can compare it to a 30-year T-bill. Tax benefits. There's the federal tax credit, which is 30% right now, up until the end of 2019. So if you have a system, it needs to be installed and commissioned before midnight, December 31st, 2019. At January 1st, 2020, that tax credit bumps down to 26%. Then it bumps down again, and then eventually sunsets. There might be some sales tax exemptions, maybe some property tax exemptions, so on and so forth. If you're a business, you can take advantage of the accelerated depreciation rates. So this system is you can accelerate the depreciation and write off the entire cost of the system over a period of 5 years, plus take the federal tax credit. So essentially, you're paying for that system, or you're getting paid for that system in the form of a tax credit. So here's that federal tax credit, renewable energy tax credit. This, what we see, applies to residential. Commercial is not going to sunset. It's going to remain at a certain cost. All right. So to get the 30% federal tax credit, you need to have the system installed by December 31st, 2019. Then it rolls down to 26%. By the end of December 31st, 2020, you need to have that installed, and then it bumps down to 22%. After December 31st, 2021, it goes to 0% federal tax credit. So if you're going to jump off the fence, you got to do it now. Or if you know somebody that's is kind of a fence sitter, kind of thinking maybe doing it, now's the time to do it. Resale value. So what is it? If I put this $15,000 system on my house, offset my electricity, all or a portion of it, how does it increase the value of my home? If you compare, there was a study done in California. If you compare two houses side by side in a suburban community, one has solar, one does not. The one that has solar sells at a significantly higher cost than the one that without solar. Other factors to consider: equity. How much have you paid into this system? Are you going to take out a loan to pay for this system? And then degradation. So the system is going to degrade over time with age based upon heat and photo degradation. And that's going to be 0.5% per year. So we're going to lose our production over time. And then, as I said before, in 30 years' time, I'm going to have 80% of my original production still on the rooftop. Other options, if you're in a rural area or a farm or agricultural business or in a rural community, you can apply for this REAP grant. And this is a competitive grant. I don't know how many they do a year, but it pays for 50% of the cost. And that's a really good deal. If you are in a tribal nation, you can apply for federal grants as well. I'm aware of a number of tribal communities that are putting solar on anything that doesn't move. Let's see what else. And then DOE loans. Some communities, like the city of Milwaukee and Madison, both have solar loan programs through credit unions. So that stuff is around. Actually, that started in Illinois, this credit union low interest loan scheme. So you might want to check with the local credit union as well. Power purchase agreements, third-party owners, they third-party developers. They own the system, they install it, they maintain it. You just buy electricity off of that. That's going to be like the system that KCC is going to have, the 2 megawatt system. Some investor is building it, they're going to own it, they're going to operate it, but then KCC is going to buy the electricity off of that. And at the end of 10 years' time, more than likely, the system owner will donate that to the college, and then they can take additional tax write-offs. And then the college can reap the benefits of owning that system. And that's a really good deal. Some states have, you can't have third-party ownership in all states. Most states you can, not all states allow that. Leasing is another kettle of fish also, where someone else owns this PV system and you just buy the electrons off of it. Or the utility, you the homeowner install the system and you sell electricity to some other entity and they resell it. So there are stuff like that out there, but it depends on the state, and I'm going to find that information out in DeSerUSA.org. Community financing, there's this PACE financing on occasion that you can see. There's a few states that have this. So the community loans you the money to install this system, and then you pay that back on your property taxes, and then that property tax goes with the home. So if you leave in 3-4 years, then you're done. The new homeowner keeps paying on that system until the loan is paid off. And that's a pretty good deal too. There's group buy schemes out there. Midwest Renewable Energy Association started this, and now there's a number of clone group buys out there. So the idea is that you group together a bunch of homeowners that are interested in a solar electric system. You group them together, put it out for a bid, and then one installer gets the contract, and then they are able to go out and buy larger quantities of equipment at a lower rate. So, and what I feel the advantage of this program has done has taken the people that were interested in putting in renewables but didn't know where to start. And it bundled them all together and got them off the fence and made them do something. And now we have all these homes that have solar electric on. They talk to their neighbors, people in the neighborhood see it, they talk to the homeowners, they kick the tires, and they feel more comfortable with this technology and are less exposed psychically or psychologically when they go out and try to go through this process too. So this is an old slide, but this is just one group buy from Milwaukee, and I can tell you that the total sales or the total capacity that has gone in from that program in Milwaukee to date is well over 1 megawatt of electricity, of rated capacity. And this program has happened in northern Wisconsin, Minneapolis, Madison, Appleton, Iowa City, Iowa, Cedar Rapids, Iowa, Quad Cities, Bloomington Normal, Champaign-Urbana, and other places. Kankakee was one of the first places that it kicked off at, and I don't know how many eventually came out of that. Non-financial benefits of PV, and we can quantify this and put a dollar value to CO2 emissions that are reduced. We can compare it to acres of trees that are planted or saved, water quality, health costs, energy independence, and grid stability. So the University of Minnesota did a study on this, and they put a value to this kilowatt hour that we're producing off of renewable energy. And they value that at 40 cents, the value of it. So every time we produce a 1 kilowatt hour of electricity, it's worth 40 cents because it's cleaning up the environment, it's reducing health risks, it's keeping the water clean, etc., etc., etc. So when we pay our utility bill, we're not paying for these externalities, these extra costs that are hidden. We pay for them in our taxes, in our health, in our polluted water, and the sort. So what we produce has a value. So there you go, gang. We are done, and as I say, we will take and do some exercises in class. If you could take a look at this presentation, get an idea of where I'm going, and then we'll take and do some exercises in class, and then go out into the shop. Anyway, hope all is well. Stay warm, and we'll talk to you later. Bye bye.